So you might be wondering, who am I and why am I giving this talk? Because I wasn't actually an author on this paper. My clinical role is as a pediatric plastic surgeon at Boston Children's Hospital, but I also spend a good chunk of my time working with the simulation program at our hospital. It's a unique program that houses everything from team training and simulated scenarios to facilities testing, 3D printing, and engineering of novel devices and procedural trainers. And because of the wide variety of disciplines that we have in this program, a lot of innovation happens. My role is primarily with the engineering team, where I'm an associate clinical director, and we have two basic arms. One is 3D printing and virtual planning, and the other is engineering with a focus on device development. And it was this group, the 3D printing and engineering team, that worked with a group of my clinical colleagues, Dr. Gansky et al., to preoperatively plan the case that inspired this talk. But before I get into detail about some of the unique possibilities that virtual surgical planning and 3D printing actually have to offer when they come together as simulation for you as a plastic surgeon, I'd like to take a step back and talk a little bit about where we've come from and how we got to the point we're at now. So 3D printing is a catchy phrase. You're likely to hear it in a lot of different arenas, both personal and professional, but you may not know what it actually means and what the variations in the process are. So in very simple terms, 3D printing is a way of taking a three-dimensional object and making it from a digital CAD or computer-assisted design file. So to prepare a digital file for printing, a 3D modeling software slices the digital model into hundreds or thousands of horizontal layers, which can be conceptualized kind of like layers on a CT scan or MRI. So they're two-dimensional objects that get put together as a three-dimensional object. When the sliced file is uploaded into a 3D printer, the object is built by one of two processes, either laying down successive bits of material in two-dimensional successive layers, or by using a laser or light to cure either a liquid or fuse a powder to create a three-dimensional object. And so this GIF file, I think, is a great example of how CT images are so well suited for making three-dimensional objects using printing. So the last decades brought about an explosion of interest in 3D printing in general. If you look in PubMed in the last decade, in 2010, we started with only 61 publications that involved 3D printing, and that grew exponentially over the next 8 years. And in 2017, there were 1,700 publications about 3D printing. And that trend has happened in healthcare as well, so it's borne out really in every aspect of what we do. And particularly for interest in research into 3D printing and plastic surgery, we've had that same trend. In 2010, there were 6 to 8 publications for the first couple of years, and it's grown exponentially to 271 publications last year alone. And I think it really serves as evidence of the rapid acceptance of the immense potential value that 3D printing offers in our specialty. So that wealth of publications has really underscored the advantages of using 3D printing in plastic surgery, and those range from things like opportunities to teach and practice procedures prior to going to the operating room, increased operative speed and decreased complications, which all come together to decreasing cost, better understanding of patient-specific pathology and anatomy, customized facial implants and facial prostheses, and this whole new wave of bioprinting. So now people are 3D printing lots of materials that can be used as implants and scaffolds, and I think that's really going to usher in this whole new wave of reconstructive opportunities for you guys as plastic surgeons. At the same time that 3D printing has been gaining traction and advancing how we practice as plastic surgeons, virtual surgical planning has been serving a very similar purpose, but in a different way. VSP uses a digital image generated from a CT or MR, very similar to 3D printing, and then a software platform is used to simulate osteotomies or other surgical maneuvers to optimize the final result through a process of precise pre-planning. Interest in VSP has grown over the course of this decade, although publications about VSP have grown linearly as opposed to exponentially as we've seen with 3D printing. And I think this is probably for two reasons. One, the earlier availability of VSP to the typical plastic surgeon, as well as its earlier cost effectiveness. And part of that's been because most of the commercial vendors we work with, SIMPeds, KLS, etc., integrated VSP early on into their offered product, and it's usually at no cost to you. The advantages of VSP are very similar to those of 3D printing, namely increased precision, accuracy, efficiency executing a variety of surgical procedures, particularly things like orthognathic surgery and craniofacial surgery, where VSP is really considered to be the gold standard. But you really get the most out of these technologies when they're used in combination, and so this really gets to what we're talking about with the idea of multimodal simulation. So some of the unique benefits of VSP include things like limitless movements and precise accuracy of volumetric measurements, as well as cost effectiveness, because if you already own a software package like Materialize Mimics or other open access software, you can do almost anything. With 3D printing, the benefits are things like having a tangible haptic model, being able to use the actual instruments you're going to use in an operation to do a procedure. But really, I think the benefits come from the similarities between the technologies and what they have in common. And by using those similarities, you can really kind of advance what you do. So both VSP and 3D printing can be used on digital images that are created from a CT or MR. Both can be used to better understand patient-specific anatomy. Both can be used for surgical planning and for simulation. So combining 3D printing and VSP maximizes the potential impact of both. So you're likely to already see this if you do reconstructive surgery, where most of the hardware vendors offer opportunities for VSP and also offer opportunities to 3D print cutting guides and other models that you can use during your procedure. But the combination of VSP and 3D printing offers the opportunity to test out new kind of out-of-the-box ideas before you ever operate on a patient. So this young lady is a patient I met early on in my practice with a condition called ectopia cordis. So this is essentially like an omphalocele of the heart, and it's pretty rare. And when she was an infant, they tried multiple times to put her heart back into her chest. But because of her small intrathoracic volume, every attempt failed because it would ultimately compress her major vessels. So when I first met her, she had a skin graft basically on top of myocardium and was having increasing trouble with graft failure, infections, wounds, things like that. And so I thought, well, this might be a great opportunity to try something new with reconstruction. And it came to my mind that we'd try chest wall distraction, but that was kind of a novel thing. I couldn't find much about it in the literature. And I'm not a total cowboy, so I wanted to do some hypothesis testing. And so that's where this marriage of VSP and 3D printing comes in. So we started by creating a digital model of her chest with all the major structures, and figured out that if we expanded ribs 4 through 8, we could potentially increase her intrathoracic volume to the point where we could put her heart back in. But one of the problems with VSP is that in cases like this that are unusual, not following some pre-planned methodology, you can do almost anything, even if it's not something that is physically possible to do on a real patient. And so knowing this, I'm just going to try to move that out of the way. Knowing this, we didn't jump into operating on her. We took that digital model and then made a life-size 3-dimensional model using 3D printing. And that gave us the opportunity to try out some different hardware sets, try out some of the available distractors, and ultimately come to the conclusion that we wouldn't be able to make the cuts or achieve the vectors of distraction necessary to do this safely. And so we didn't end up operating on her. But 3D printing and VSP really gave us the opportunity to explore something we frankly never would have considered, and then make the decision before actually operating on this patient that it wasn't the right thing to do for her. But the combination of VSP and 3D printing can also yield major successes for these kinds of unusual cases, such as this patient who is the inspiration for this talk. So this is a young man who is born with an encephalocele that was thought to contain an unusually large portion of his functional brain. And because of that, it couldn't simply be removed. Our surgical team needed to increase his intracranial volume enough to actually accommodate and allow for good tissue perfusion of that brain tissue. So rather than go to the operating room simply with the idea that we'd do the best thing possible in terms of expanding his skull, our surgeons went through an iterative process with our simulation engineering team, first starting with a digital model, and we did some volumetric analyses to determine the amount of volume expansion we'd need to put that brain tissue back in, and then 3D printed a model, did the procedure on the model, and then took the model back to the engineers, rescanned what we planned to do for the operation, and determined that we actually hadn't expanded the intracranial volume nearly as much as we thought. Took that opportunity to then make some new osteotomies and barrel staves on our operated skull, rescan, and work through an iterative process to a point where we felt that we had sort of theoretically confirmed both on the model and through the digital analyses that what we were bringing to the patient was going to solve the problem. And that was translated intraoperatively to the patient with a successful result. So now you probably have some ideas about how you as a plastic surgeon can use VSP and 3D printing in your practice, but how do you actually start incorporating them? Well, there's a number of no or low cost ways to dip your toes into 3D printing. For example, if you do some bony work, you probably can already work with a hardware vendor in your area to make 3D models, to do some virtual surgical planning, to print cutting guides. But if your ideas are outside of the bony realm, there are a number of commercial outlets that will 3D print models for you, and many of them will actually do some device rapid prototyping to help you explore different types of ideas. Moreover, there are many colleges and universities that have kids who have 3D printers on their desk, like the one shown here. And you can probably find somebody who can do what you're interested in at no or low cost. I always joke that you could probably just bring a 6-pack of beer and get a college kid to do most of this for you. If you are working in a large institution, whether it be academic or military, you probably already have some of these resources for VSP and 3D printing available to you in your hospital. A lot of times these resources live within the Department of Radiology because they're already using the kind of digital imaging software that's necessary to do what you want to do as part of their daily routine. So before you dive in and start to build a center for yourself, it's worth collaborating with people who are already doing that. And the reason why is so that you can both learn from them, but also learn what the minimum resources needed will be. You don't necessarily need to jump into buying the fanciest thing or trying, the most complex thing. There are a lot of simple ways to do it. For example, Embody 3D is an open access software. Blender is another open access software, and they allow you to do some basic segmentation at no cost. If you want to do something really fancy, you're going to need a software package like Materialize Mimics, which your radiology department may already have, and that will allow you to do a little bit of a higher level of VSP and segmentation, combining images, and can run you anywhere from $7,000 to $30,000. Similarly, you don't actually need a large investment to jump into actually making 3D prints. The amount of the investment is really a function of what the purpose of your print is, and the closer your print gets to the patient in a literal sense, the more costly it's going to be. For example, if all you want to do is simple modeling to understand anatomy, to educate patients, and to practice surgical procedures, you can do this at really low cost with things like a basic extrusion printer, which just spits out some material and makes a three-dimensional shape. If you actually want to print cutting guides that are going to come into contact with the patient, it's going to be more expensive because it needs to go through a process that's actually regulated by the FDA. And if you're really going to get fancy and dive into the tissue engineering realm, that's where it really starts to get expensive. And I think the idea for you guys as plastic surgeons is that you can start pretty small and at low cost. I mean, some of these printers cost in the hundreds of dollars. And then you can start to work up from there to explore ideas and kind of change how you practice. So just to conclude, 3D printing and VSP already have great utility for you guys as plastic surgeons, but it's really the marriage of these technologies that provides you with some unique opportunities to explore your more difficult and impossible cases, such as through testing feasibility of ideas, like we've shown here, but also through working through procedures and iterations until you can be certain that the result you bring to your patient and the solution you bring is really going to give them the most successful outcome possible. Thank you.
Thank you, Dr. Rogers. And if anyone has any questions, please come to the mic in a minute here and ask a question of Dr. Rogers.
Thanks very much for a fascinating and a great presentation. we're a big fan of VSP at NYU, and a lot of our faculty use it. And recently, they've kind of been expanding on this with other specialties and getting them to use it as well with us, mainly in like extra patients or resections with orthopedic surgery. And we found that they've been able to do much more precise resections of hip tumors, arms, and things. And it's actually gone quite well as far as an interdisciplinary thing. Have you had any experience with trying to expand this to other specialties and how their acceptance of it, and how is that going?
So our program is totally interdisciplinary, and it's been like that from the start. Our simulation program was really born out of critical care medicine, and then this engineering component came in as I was starting in practice about 6 years ago, and they work with all of the surgical and medicine and nursing disciplines. And I think one of the challenges as you start to do this yourself, you find how time consuming it is. I think there's far more demand than we have time to do it, which is why I think a lot of times we're just working on the most challenging or difficult cases. And I think that, it's the reason a lot of people are starting to buy these software packages and start doing it themselves. It's not that it's hard to do, it's the time that you put into it.
Thank you.
Good morning, Evan Garfine from Montefiore. That was a great talk. I really enjoyed it. I think having been around virtual surgical planning for over 10 years now, we have a pretty good idea of how to handle bone, and both from the printing side and the planning side, both the engineers, the radiologists, the surgeons, we all sort of get it. I think the next frontier is soft tissue, and I was wondering if you have any thoughts or insight onto virtual surgical planning for soft tissue. I think it's a lot more challenging for a variety of reasons.
It is a lot more challenging. I'd say we've kind of taken more of the high fidelity approach to managing soft tissue. What we tend to do is more 3D printing of bony and soft tissue constructs and do more silicone modeling and things like that to better replicate the mechanics of soft tissue. But there are a lot of good studies that are going on now that are looking at how tissue deforms, and I think that once those are complete, we'll have a better idea of how to actually simulate tissue movements. And the challenge is really that it's different from patient to patient. And I think for my practice, I use silicone a lot more than VSP just because I like the tactile aspect of it. But I think that from the standpoint of cost effectiveness, that's where we need to go.
Thank you.
Okay, any more questions?
Hi, I'm Aaron Weinstein. I'm not a plastic surgeon, but I have one question for you via the internet from Sam Lynn. So Sam wants to know, what is the next thing in 3D printed plates?
There are lots of next things, and the challenge about doing that in the U.S. is that it's all regulated by the FDA. I had a great trip to Taiwan last year where they're doing a lot of 3D printing of titanium and various bioresorbable things. I think in the U.S. that's where we need to go, is print bioresorbable plates, but it's hard to get that kind of stuff through the FDA. So I think it's the next step, but I don't know when that step's actually going to happen.
While we're waiting, Sam just sent another question. He said, how can you cut the time down for VSP planning when doing surgical planning for a case?
It depends on your case. If you're doing the planning yourself, I think that you're really adding time, but you're also adding precision, and you're cutting down on complications. But I think that when you have these kind of, I don't want to call them cookie cutter cases, but the kind of things that VSP is used for all the time, by developing algorithms that do it for you rather than having a person who does it for you, that's really where we're going to cut down on time.
Thank you, Dr. Ron.